Welcome to today's Explainer. We're diving into a revolution that is, quite frankly, entirely reshaping the scientific world. For centuries, chemistry basically meant test tubes, Bunsen burners, and getting your hands messy with physical experiments. But today? Well, it turns out the ultimate lab tool isn't made of glass at all. It's actually made of code. We are talking about Python. It's the programming language that is brilliantly bridging the gap between traditional chemistry and cutting-edge artificial intelligence.
So it really all boils down to one fascinating question. How do we teach a computer, a machine literally made of silicon, to actually understand the intricate, messy nuances of chemistry? The secret? It's data and coding. Those are the essential keys to unlocking entirely new chemical discoveries. They allow us to predict properties and even design new molecules without ever stepping foot in a physical lab.
Okay, let's dive into our roadmap for today. We'll start with why Python rules chemistry. Explore the essential data stack. See how RDK translates chemistry, build a real AI model, look at real-world lab applications, and finally, chart out your ultimate learning path.
Section 1. Why Python rules chemistry. The simple syntax that powers complex science.
Look, Python is basically the undisputed king of AI-driven chemistry. Why? Because it's open source. It boasts a massive scientific community, and crucially, it is extremely beginner-friendly. Storing basic chemical information is surprisingly intuitive. You can save a compound's name simply as a text string, or its molecular weight as a decimal float. Python's syntax actually reads a whole lot like ordinary English, and that's a game changer, because it means you spend way less time fighting complex code and a lot more time doing actual science.
Moving right along to Section 2, the essential data stack, upgrading your digital lab equipment.
Now, if we're going to do chemistry on a computer, we absolutely need some heavy lifters. Enter NumPy. Think of NumPy as your high-powered, supercharged digital calculator. Instead of doing manual spectral math, which, let's face it, could take weeks, NumPy handles massive matrix operations in literally milliseconds. It is the raw computational muscle behind almost all modern molecular simulations.
And right alongside NumPy, we have Pandas. If NumPy is your calculator, Pandas is your brilliant, perfectly organized digital lab notebook. Let's be real here. Physical lab books get messy, and experimental data can be completely chaotic. Pandas brilliantly takes those messy CSV files and experimental measurements and just instantly neatens them up into highly readable rows and columns. It makes handling massive chemical data sets an absolute breeze.
Section 3. RDKit, translating chemistry, turning molecules into machine code.
Here's the thing. Computers don't inherently understand what ethanol is. They don't have a clue what a carbon ring looks like. That is exactly where RDKit comes in. It's basically our chemoinformatics microscope. It performs this incredible translation, taking a standard chemical name, like ethanol, and converting it into a binary molecular fingerprint. Suddenly, a physical molecule becomes a pattern of ones and zeros that an AI can actually digest and analyze.
But it doesn't stop there. RDKit also calculates key molecular descriptors. It extracts numerical features like a molecule's weight, its log P, its polar surface area, and how its hydrogen bond donors behave. The crucial takeaway here is that we are converting real-world physical properties into structured math. And that math, that is the exact fuel our machine learning models need to function.
Section 4. Building your first AI model, predicting chemical properties with Scikit-Learn.
Okay, before we actually build anything, we've got to establish the golden rule of machine learning. You absolutely cannot test your AI on the exact same data you use to teach it. You must split your data set. So you use 80% of your chemical data to train the model, letting it find all those hidden patterns, and you hold back 20% to test it later. This is absolutely crucial because it proves whether your AI is actually predicting new chemical properties accurately or if it's just lazy and memorized the answers.
Building the model itself using Scikit-Learn follows a beautifully logical 5-step rhythm. First, you import your libraries. Second, load up that chemical dataset. Third, define your features. Fourth, train the model. And finally, step 5, you ask it to predict a completely new property, like the solubility of a brand new compound. With our digital tool belt fully equipped, it really is that straightforward.
So once you make those predictions, you need to know if they're actually accurate, right? We do this using the R-squared score. And wow, look at this result, 0.95. What's really interesting here is that a perfect score is 1.0, so hitting 0.95 means our AI is incredibly successful at predicting chemistry based entirely on the patterns it just learned. It's actually working.
Section 5. Real-world lab applications. Python outside the classroom.
Now, these aren't just academic exercises. These exact tools are revolutionizing actual labs globally right now. Instead of spending decades physically testing drugs, Python accelerates drug discovery by virtually screening millions of compounds overnight. It automates spectroscopy, pushes battery science forward in materials science, and, maybe most incredibly, it actually guides robotic arms and laboratory automation to synthesize new chemicals perfectly, every single time.
But hold on a second. Before you run off and try to automate your entire lab, we really need to talk about what goes wrong. Because there are some major, common beginner pitfalls ahead that can completely derail your chemical AI models. Listen, even the absolute most advanced model will fail spectacularly if you feed it garbage. Using dirty, unclean data with missing values, that's a guaranteed recipe for failure. Then there's overfitting, where your model just memorizes the training data instead of actually learning the underlying chemistry. Using too few samples, ignoring evaluation metrics, like MAE, or choosing poor, irrelevant features will completely derail your predictions.
And that brings us to Section 6, the ultimate learning path, your journey to AI chemistry.
My advice? Don't try to learn everything at once. Just follow this timeline. Start with Phase 1, simple Python basics, variables, and loops. Then, in Phase 2, learn to handle data with NumPy and Pandas. In Phase 3, start translating those molecules with RDKit. Once you have that data sorted out, hit Phase 4, building predictive models with Scikit-Learn. Phase 5 is where you finally apply this to actual chemistry projects. And finally, Phase 6 takes you into advanced deep learning with tools like TensorFlow or PyTorch. It's a step-by-step evolution, and honestly, it's completely doable.
The laboratory of tomorrow is literally being built today, and the foundational language of that laboratory is Python. You've got the roadmap now. The tools are completely open source, and they are just waiting for you. So I'll leave you with this one question to think about. Will you be the chemist who simply runs the experiments, or the one who programs the AI to discover them? Thanks so much for joining me on today's Explainer. Now go write that first line of code.